Hello everyone, this is Jianxin Wang, who's speaking, and another people Zizhang Xu from Group 24. This is our final project. For our simulation, we choose to simulate a Chinese restaurant which is pretty popular for Chinese students in the university. It's called Wanjiaxiang, and down here are several pictures for you if you're not very familiar with this restaurant. For this project, we have two goals. One is to see how changes in arrival rates, normal hours versus peak hours, can affect the number of people that has been served during a certain amount of time. And another goal is to see how change in the number and size of tables. For example, we can change half of their tables of size 4 to twice the number of size 2, and what this kind of change can affect the number of people served. These are two videos we took at the restaurant. On the left side here is showing the size and number of their tables. There are actually 7 tables of size 4 on the left and right side in the restaurant. And in the middle, there are a large table, as you can notice, but it is actually combined by 4 tables of size 4. So for our simulation, we just simply assume there are 11 tables of size 4 in total. And on the right side here is a pretty fast video, but the original length is 12 minutes. And during the entire video, there are approximately 12 or 11 people entering the restaurant. And this video is taken at 5:30 in the afternoon. And so the arrival rate during peak hour is pretty high. So let's get to the actual policy that we determined for our project. During normal hours, 1 people entering the restaurant per 4 minutes. And during peak hour, 1 people enter the restaurant per 1 minute. And people come as group of 1, 2, or 4, as we assume, with probability 0.4, 0.4, and 0.2 respectively. And groups do not share tables. And as we just mentioned, there are 11 tables of size 4. And when people usually order 1 meal, that means if there's a group of size 4, they will order 4 meals. For chiefs, there are 3 chiefs, and each chief serves 1 group at a time. And for each meal, they will spend 5 minutes on it. And since chiefs are pretty efficient, the groups that are waiting often do not leave the restaurant. And but there's a special case. When a group of people came in and see if all the tables are occupied, they would just simply leave. And if a group are served by a chief, they will eat their meals for 30 minutes and leave. And for the inter-arrival time of customers, we will use Poisson distribution. And the last policy is that if a chief can finish the meal for a group before next arrival event, he will just take a break. And during this gap time, we will look for another idle chief that can serve for another waiting group. Okay, this is the event graph that I make. For you to easily understand this, we divide this event graph into 4 sections. And the general logic is to see is this. First, we set up all the size, numbers of tables, and everything else. And upon the arrival of a group, we want to see if there's a empty table for them to sit. And after that, we want to look for a chief that can serve for a waiting group. And after that, we enter section 3 right here. In this section, we look for a table that can be available before next arrival event, so that it can become an option for next group to choose. And the same, we look for in the end, we look for a chief that can be available before next group arrives. And after all these, we can just return to the arrival event and follow the same procedure again and again. Okay, so let's get to our results. First off, we want to see how changes in arrival rates can affect the number of people being served. During normal hours, we run for 412 minutes, which is 7 hours. And the expected number for the Poisson distribution is actually 1/8, because the average group size, as we stated before, is 2. and on average, 1 people enter the restaurant every 4 minutes. So the expected number is 1/8. And on the right here, you can see during 7 hours, 97 people get served. Okay, and during peak hours, we run for only 80 minutes because the peak hours is usually short. And the expected number using the same calculating method is 1/2. And the result is that during 80 minutes, 40 people get served. So an observation for these two different results is that during the rate that people get served during normal hours is actually much higher than the rate that people get served during peak hours. This is because during peak hours, for most of the time, all tables are actually occupied. So there are many cases when people enter the restaurant and cannot find an empty table, so they will just leave and not get served. Okay, and the second result, we want to see how changes in number and size of tables can affect the number of people being served. This is actually hypothetical because we cannot literally change the size or number of tables in the restaurant. So we'll just run the simulation and see how it will make a difference. Okay, and similar, during normal hours, we run for 7 hours with the same expected number, and the result is really close to what we have before. It's 96 people get served during 7 hours. And for the peak hours, we run for 90 minutes with the same expected number, and it's still very close to what I had before. It's 41 people get served during peak hours. So our conclusion is that the changes in number and size of tables does not affect much to the result, but instead, what affect the result the most is the change in arrival rates, which is obvious and intuitive. And finally, we want to discuss some possible sources of error. First off, at the restaurant, there are actually 7 tables of size 4 and a large table of size 16 in the middle, but instead we just simply assume there are 11 tables of size 4. This is going to make a difference because the large table in the middle will probably change the people's choice of seating. And the second is that we assume that no groups share a table. But in some cases, people do share a table because, like for example, there are some groups, like 2 groups of people enter a restaurant, and they recognize each other because they are familiar with each other. So they are probably willing to share a table, and thus will make a difference. And for inter-arrival rates, we'll use this Poisson distribution. But there are actually many other factors entering the arrival rate. For example, the weekday or weekend. So the arrival rate might not follow Poisson distribution exactly. And when all tables are occupied, people might not directly choose to leave in real situations, because like for during peak hours, when people see all tables are occupied, they might choose to like wait for 3 or 4 minutes until there's an empty table, and they can sit there to eat. So in the end, there might be more people get served. And the last possible source of error is that in real situation, chief might just directly continue working and do not take a break if they can become available before next arrival event. So these are everything we got for this project, and thank you very much for watching.